Hello everyone, welcome to Pen and Paper. Today we are going to find the equation of this curve. Actually here we are having two poles and a rope, or let's say a wire is hanging between them, and we can clearly see that a wire is sagging. So it is often assumed that whenever a wire is sagging between the two poles, it takes the shape of a parabola. But actually, it's actually a catenary and not a parabola. So today we are going to prove that this equation is actually a catenary. And what is the equation? What is catenary? How its equation looks like? So today we are going to prove this using both mathematics and physics. So let's get started. Here, since this is a rope between the two poles, let's say we have some small segment. I'm considering a small segment of the rope. Okay, I'm considering only a small segment of the rope over here. So this x coordinate is x. The x coordinate of this is, let's say, x plus delta x. Okay, so what I'll do, I'll draw this segment again and I will draw a free body diagram. I'm going to draw free body diagram of this segment of this rope. Okay, let me draw it with a red color. So if I am having this segment as this way, okay, if I'm having this segment as this way, this is my segment, small segment. Now I'm going to draw all the forces acting on it. So here, these are the tension forces, these are the tension that will act away from the body. And let's say we are having, I'm having this angle, I'm having this angle as alpha at position x, and this angle I'm having as alpha at position x plus dx. Because if you look at this diagram, the two segments, one end of the segment is as at position x. Okay, one segment is at position x and the other segment is at position x plus delta x. Fine. So over here, so here the tension force that will act at position x plus delta x, I will write that as x plus delta x, and the tension force that will act at position x is, I will write it as Tx. Now what I'll do, I'm going to resolve the forces in x and y components. Okay, okay, so now in x direction, the forces acting in the x direction, since it is in equilibrium, I can write t at position x plus delta x into cos of alpha at position x plus delta x, fine, minus tx cos alpha x, the x component of this tension, that is tx cos alpha at position x, fine, and this is equals to 0. Now what I'll do, I'll divide both side. I'm going to divide both side by delta x, fine, and I'm going to apply the limit delta x approaches 0. Now the reason why I am applying this limit is that I need to convert this into differential. So when delta x approaches 0, delta x would become dx. If you look at this expression, this is the differentiation of tx cos of alpha x. Reason being, we write f dash of x as f of x plus delta x minus f of x divided by delta x and limit delta x approaches 0. This is f dash x. So similarly, using this, here it was fx, so here it is f dash x, here it is tx cos alpha x, so it would be differentiation of this tx cos alpha at position x. Reason why? Because here it was fx, so here we wrote f dash x, here it is tx cos alpha x, so here we are writing differentiation of tx cos alpha x, and obviously this delta x is going to become dx as we have applied the limit delta x approaches 0, and this is equals to 0. If differentiation of something is 0, that means that quantity is constant. That means tx cos of alpha at position x is some constant c, fine. So from here we are getting tx to be equal to c by cos alpha x. Okay, we are going to make use of this relation later. Now I'm going to resolve the forces in y direction. Okay, now let me resolve the forces in y direction. Let me resolve it this side. Okay, so here in y direction, fine. Here what I'll write, here remember, here mass, if this is having mass m, gravity is acting on it, so force mg is acting on it, so I will write mg is equals to, now we are going to take the vertical component, so t x at position x plus delta x sine of angle alpha at position x plus delta x, fine, minus t tension at position x sine of alpha at position x, fine. Now here also what we are going to do, we are going to divide both sides by delta x. and we are going to apply the limit delta x approaches 0. So delta x would become dx, and this quantity would be differentiation of this quantity, as I have shown over here, that this quantity, this quantity, this whole quantity, was differentiation of this quantity using this principle, differentiation principle. Similarly, I can write this quantity, this whole quantity, as d of this quantity, differentiation of this quantity, that is tx sine alpha at position x, fine, divided by this delta x is going to become dx, and here we are having mg by delta x. Okay, but remember, there is one more thing. When we are applying the limit delta x approaches 0, so this segment would become of differential length dl. Okay, and here we had lambda as mass per unit volume, a as area of the cross section. If a is the area of cross section and lambda is mass per unit volume, so from here we need to find out mass. My mass would be equal to lambda is mass per unit volume, a is area of cross section. So volume is going to be volume, let me write the volume over here. Volume is going to be area of cross section A into length of the segment, that is dl. So my mass is going to be mass per unit volume, so lambda. Okay, and here A dl, because this is the volume. If I multiply g both side, this is my force mg, and if I divide both side by dx, so if this constant, this whole thing, lambda a dl, actually not lambda a dl, but let me erase this. Okay, so this lambda a into g, this is going to be constant. So let me represent lambda a into g by some constant, let's say c1. Okay, so from here I am getting mg by dx to be equal to c1 dl by dx, and here we had this quantity to be equal to mg by delta x, so this delta x would become dx. So mg by dx is c1 dl by dx. So here I will write c1 dl by dx, fine. And we had the value of tx over here. Tx over here was c by cos alpha x. So I will replace, what I will do is, I'm going to replace this tx with this c by cos alpha x. Fine. So if I replace tx by c of cos alpha x, this would become equal to differentiation of c tan alpha x by dx, and here we are having c1 dl by dx. But remember, the length of the segment L is given by integration. L is the length of the arc, so length of the arc is given by 1 plus dy by dx whole square into dx. Okay, so if we differentiate both sides, I will get dl by dx to be equal to root under 1 plus dy by dx whole square. And this is very standard form, but you can prove even this also. How? Let us see. Let's say we are having some segment of length, differential length dl. So this x coordinate would be delta x, or let's say dx. This is going to be dx, and this is going to be dy. And for differential length, this will act as a hypotenuse. So dl can then be written as root under dx square plus dy square. Fine. Now if we divide both sides by dx, so this would become dl by dx is equals to 1 plus dy by dx whole square. And if we integrate both sides of this expression, we are going to get this expression. Okay, so from here we are getting this dl by dx to be equal to this quantity. So over here I am going to substitute the value of dl by dx. So C1 dl by dx is this quantity, 1 plus dy by dx whole square, and this is equals to d, and tan of alpha x is actually dy by dx. So I am taking this c outside, and d of dy by dx, because this tan of alpha x is actually dy by dx. So differentiation of dy by dx would be d2y by dx square. Fine. Now what I will do, I will put dy by dx to be equal to t. Fine. And now what I'll do, I'll differentiate both sides. So if I differentiate both sides, I'm going to get d2y by dx square is equals to dt by dx. So here I will put t. So here I am getting 1 plus t square root under. Fine. And here what I'll do, I'll divide both sides by, I'm going to divide both sides by c. So this will get cancelled. Here this is c. So 1 plus t square and d2y by dx square. d2y by dx square is dt by dx. So this becomes dt by dx. This can be written as, here c1 by c, I will write this c1 by c as some constant a. Okay, so this can be written as a times dx is equals to dt by root under 1 plus t square. Now let's integrate both sides. So the integration of this quantity is in a very standard form. This is ln of t plus root under 1 plus t square. But still, if you want to know that how this standard result comes, so what you need to do, you need to replace this t with tan theta, and ultimately you will arrive at this solution. But this is a very standard integration, so it's advised that we should remember this result. Now this is equals to ax, the integration of over here is going to be ax plus some constant c. But dy by dx is equals to t. At x equals to 0, at x equals to 0, I am saying that dy by dx is going to be equal to 0. That means the slope is going to be 0 at x equals to 0. And we can easily check this. We can easily check this. Here, obviously the slope, if I draw a slope over here, if I draw this slope over here, it is going to be parallel to x-axis. So obviously dy by dx is going to be 0 at x, at this x equals to 0. Fine. So let's go back to the final equation. This is a final equation. So I'll put x equals to 0. So here I will get c, and here I will get ln of 1, that would be 0. So my c is going to turn out to be 0. So this expression then becomes ln of t root under 1 plus t square is equals to ax. Okay. Now what I'll do, just for convenience, I will replace a with equal to 1 by b. Just for convenience, it is not going to make any difference. So here, let me erase this a and let me write it as 1 by b. 1 by b. Now let's take exponential, raise this to the power e both side. Okay. And we know that e to the power ln m is equals to m. So this would become t plus root under 1 plus t square equals to e to the power x by b. Okay. Fine. Now let's rationalize this. If I rationalize this, so what I'll do, I'll multiply both sides with by t minus root under 1 plus t square, and divide also by t minus root under 1 plus t square, and this is equals to e to the power x by b. So I will multiply both sides by e to the power minus x by b. So this quantity over right hand side would become equal to 1. Fine. And here this quantity is going to become, this numerator is going to become minus 1, here e to the power minus x by b, and here I am getting t minus root under 1 plus t square. So on cross multiplication, if I cross multiply this, what I'll get is, on cross multiplication, I will get e to the power minus x by b is equals to t minus root under 1 plus t square. Now what I'll do, I will add this and this equation. If I add these two, what I'll get, this e to the power x by b and minus e to the power minus x by b. So e to the power x by b minus e to the power minus x by b. Okay, and this is equals to, if we add this expression and this expression, so we are going to get 2t. Fine. So from here we are getting t to be equal to e to the power x by b minus e to the power minus x by b by 2, and t, remember our t was equal to dy by dx. So what I'll do, this dx, instead of writing dx below dy, I will take dx over here and I am going to integrate both sides. E to the power x by b minus e to the power minus x by b divided by 2. So if I integrate this, I am going to get y equals to, integration of this is going to be e to the power x by b, this minus and this minus and this minus, so plus e to the power minus x by b, and here 2. We need to divide, here we are having the coefficient of x is 1 by b, so we need to divide by 1 by b, so b will come over here. Okay, and some constant of integration, let's say some constant k. Okay, but if you look at the graph carefully, if you look at the curve carefully, this curve passes through origin. Okay, that means if this curve is passing through origin, so if I replace x with x equals to 0 and y equals to 0 should satisfy this curve. So if I put y equals to 0, this is going to become 0. This expression is going to become b plus k. From here I get k to be equal to minus b. So this equation then becomes y equals to b, and this expression inside the bracket, this expression is actually called hyperbolic function cos h x by b, because e to the power x plus e to the power minus x by 2 is actually cos h of hyperbolic h of x. So this expression can be written as cos h of x by b, and this k we got as minus b. So this is our final solution. We have already found that this curve is actually a catenary and not a parabola. Since this is a hyperbolic function, this representation in this way, this is called hyperbolic function. Since this is a hyperbolic function, hence this curve is called catenary. Okay, hope you like this video. Make sure to like, subscribe, comment and share. Thank you.